My name is Chris Toth, and I am on the CAB team for WSP here in Columbus, Ohio. Just for your information, the presentation can be found in the handout box, and feel free to ask questions in the chat box, and we'll try to get to as many of those as we can at the end of the presentation. So just a quick overview of the presentation. First thing we'll do is just go over some of the key highlights of the Smart Columbus Connected Vehicle environment. Then we're going to talk through a few of the things that WSP does on this project. Then we're going to go through what some of the objectives were. Then looking into some of the connected vehicle applications that we're going to deploy to meet those objectives. Talk through some of our key challenges that we came into, and quickly go through what the project status was, and then we'll answer some questions. Columbus is the capital city of the state of Ohio, and Columbus's population is roughly at 900,000, and the metro area being the home of over 2 million people. You know, by U.S. standards, it's considered a medium-sized metro area, and that actually puts us, you know, being centrally located in the eastern half of the United States, puts us within a one-day drive of roughly half of the U.S. population. So some of the key highlights of the connected vehicle environment. Connected vehicle devices enable vehicles to talk to each other and to traffic signals, and the technology that's used is called dedicated short-range communications, and that's a very similar communications technology to Wi-Fi. The plan is to deploy onboard units in over 1,000 vehicles and roadside units at 85 roadside locations. Onboard equipment consists of a processing unit, antenna, a heads-up display, and it interfaces with the vehicle and transmits information about a vehicle's location, speed, and trajectory and its size to other equipped vehicles that are in its immediate vicinity within the wireless range.
Chris, your slides aren't changing. I'm sorry to interrupt.
Sorry about that. Thanks for pointing that out. I might have some connectivity issues, so allow me to reconnect. Okay. Has it updated yet? Or am I reconnected?
I'm still seeing just the introductory slide, the title slide. Oh, there. Now you go. There we go.
Sorry about the technical difficulties, everyone. All right, so I'll continue on with the highlights of the project. So where did we leave off here? We're talking about the onboard units and roadside units. So the heads-up displays, they're going to be used in certain vehicles, and those are going to provide audio-visual alerts to drivers in certain specific situations, and I'm going to discuss some of those here in a little bit. The roadside units are mounted, you know, adjacent to traffic signals on either light posts or on mast arms along our corridors. The range of these RSUs is about 800 meters or about half a mile. The RSU broadcasts information such as the roadway geometry, the signal phase and timing, and roadside safety messages. And these messages can be picked up by the vehicles and be used by those vehicles to enable vehicle-based applications. Next, the fiber optic network provides connectivity between the roadside, our traffic management center, and other external internet-connected systems. It allows for firmware updates to be pushed to both RSUs and to OBUs, and for operations data to be transmitted back to a data repository for storage, and to be used for like traffic management purposes, potentially. We use what's called the Connected Vehicle Systems Engineering Architecture to design the connected vehicle system for Columbus. And then finally, we're implementing wireless communication security, and this ensures that we're randomizing IP addresses, and we're using digital certificates, and this ensures anonymity, and at the same time we're able to preserve authenticity of the messages and making sure all of that data is coming from a reliable source and that it is good. So what does WSP do in the connected vehicle environment? First and foremost, we are doing systems engineering for the connected vehicle environment. And so what is that? Systems engineering, cuts across many different disciplines. And the connected vehicle environment is bringing together elements of transportation engineering, network and communications engineering, or even computer engineering, among many potential other disciplines. But it's integrating all of these disciplines into a team effort, and we're able to develop the system in a way that allows it to proceed from the concept through production to operation in an efficient manner. So first, we're developing a concept of operations where we're focusing on defining user needs and the development of high-level scenarios. Then we move into our system requirements, where we're adding another level of detail about what the system must be capable of doing to meet those user needs and scenarios that we developed previously in the concept. Then on to our interface control and system design documents, where we are defining the information that is exchanged between devices that are both internal and external to the system. And then we're specifying how data is used and processed within the system to meet the requirements. So as you can see, there's some level of traceability between the concept of operations, system requirements, interface control, and system design. And this traceability, it allows us to test the system at the end and design specifications to ensure that the system is implemented, that the system that's implemented at the end of the project is directly related to the user needs that we originally derived, and that the system can solve the problem that we set out to solve. Once we completed the systems engineering process, the system was procured, and the documentation that was developed becomes a blueprint for how the system is to be built. We assisted Columbus in the development of the RFPs and provided guidance in reviewing proposals. And so we were a client representative as well, and that's the second main bullet that we have on the slide. So once OBU and RSU vendors are selected, we end up acting as a liaison between vendors and the city to ensure that the system is built according to our specifications. This is done through testing, validation, verification, and those are actually part of the systems engineering process as well. So some of the project objectives, first being improving vehicle operator safety. We noticed that along our corridors of interest that there were there are high crash corridors, and so we looked through crash data to determine that there was a lot of vehicle-to-vehicle crashes along these corridors. Some of these were intersections, and so we wanted to improve intersection safety as well. We looked through data to determine that there were a lot of speeding within school zones, and we wanted to try to reduce the speed of vehicles in the school zones by raising awareness of when those school zones are active and when vehicles are driving over the speed limit. Next was improving the reliability of transit vehicle schedule adherence. We noticed that there are certain situations where buses are falling behind schedule, and we want to try to keep them on schedule as much as we can. on our corridors. The next was that, we're trying to continuously improve emergency response times. Also reducing truck delayed signalized intersections along our freight corridors, and finally improving our ability to manage both transit and traffic. So now I'm going to talk a little bit through how our applications are going to meet some of those objectives. So our vehicle-to-vehicle applications are intended to address some of the vehicle-to-vehicle crashes that were observed along with, to address vehicle-to-vehicle crashes that are observed along the corridor. So forward collision warning, that advises a vehicle operator to take action in order to avoid a rear-end collision, in the forward path of travel. So if you're approaching another vehicle too quickly, you'll get a warning sort of alerting you to that situation, and it gives you an opportunity to react to avoid that potential bad situation. We have our emergency electronic brake light, and that's going to provide an output when a vehicle in front of you is braking in an emergency fashion. And so unlike forward collision warning, where you're typically only concerned about the vehicle directly in front of you, emergency electronic brake light is looking several vehicles in advance to provide early warning of an emergency braking situation. Next is the lane change warning, and that's going to provide an output to the driver, and that's supposed to help improve awareness of when you have another vehicle in an adjacent lane in your blind spot, so that you don't end up in a sideswipe incident. And finally, an intersection movement assist, and that provides an alert to a driver when there's a vehicle turning across its path, or you're about to turn across the path of another vehicle. With the idea being that when you receive those alerts, you'll be able to take action to avoid that situation. Now, onto our vehicle-to-infrastructure applications. These are similar to V2V, but rather than information being exchanged between vehicles, these are applications that are related to information being exchanged from the roadside to a vehicle. So our first application that we're deploying for V2I is the red light violation warning, and that's going to provide an alert to a driver when they're approaching a signal that is going to turn red. And the idea is to get that information to the driver actually before the signal changes to yellow, so that they can make an earlier decision and that they don't end up getting caught in dilemma zone, or they don't know whether to stop or go. The reduced speed school zone application is going to provide an alert to a driver when they are either approaching or within a school zone that is active and they are traveling over the school zone speed limit. So in Columbus, that's actually 20 miles per hour. So if you're traveling above 20 miles an hour, you'll receive an alert, and you have the ability to slow down, and that alert will go away. Next is traffic signal priority and preemption. This actually encompasses three different types of priority and preemption. We're going to be doing priority for both transit vehicles and for freight vehicles or heavy-duty vehicles on certain transit routes and along certain freight corridors. So we're only going to be providing priority for certain movements on those corridors for those vehicles, as well as preemption for emergency vehicles, and that is going to be at all intersections for all directions. Next is our vehicle data for traffic operations. This is actually one of my personal favorite applications because we're able to capture telemetry data from vehicles and from our traffic signals, such as the signal state from our traffic signals, and we're able to capture all that information and send it back to a data repository. And all of that data can be used for traffic management, different traffic management applications. We're not necessarily executing any applications as part of Smart Columbus or the connected vehicle environment, but some of the potential applications would be, adaptive signal timing, or putting a message up on a variable message sign. And finally, our transit vehicle interaction event reporting. This is where our transit vehicles are going to be capturing data from other surrounding vehicles and it allows transit agencies to determine, where their vehicles are experiencing certain types of situations, and can determine how they want to move forward in providing notifications to their drivers in the future about these situations. So some of the key challenges that we came upon during the course of this project, first being our map message generation. One of the easiest methods to generate map messages is to use aerial imagery. And I'm sure most people are familiar with, the imagery that's available through Google Maps, for instance, or, other online mapping systems. But what's actually interesting, and one thing that we found out during this whole process, was that a lot of this imagery is actually, there are errors, and it's not exactly, there are some minor differences between the imagery and ground truth. And in several cases, or in most cases, it could be up to several feet. And this error was actually not consistent from one intersection to the next. So we quickly learned that not all imagery is created equal. We're very fortunate that the state of Ohio has a statewide imagery program, and they recently updated their aerial imagery back in 2019. And it was found to actually be very representative of the ground truth, and we were able to confirm that using a GPS-based survey. We absolutely had to make sure that the aerial imagery that we were using to generate our map messages was accurate. Our next challenge that we have faced, and this one is a little more recent here, is the proposal by the Federal Communications Commission, or FCC, for the DSRC spectrum reallocation. So as part of this proposal, the FCC, they wanted to reallocate part of the wireless DSRC spectrum that was initially set aside for vehicle safety. The proposal takes about half of that spectrum and gives it to the unlicensed Wi-Fi, and the remaining half is to be split between DSRC, which is already used for, and a competing communications technology called C-V2X. So one of the challenges was to determine how the CVE could potentially be impacted by this proposal. We determined that for this particular project, the impacts were likely to be low, but the broader impacts are much greater, especially once more and more vehicles are equipped with on-vehicle or onboard units, and as we get more RSUs at our intersections. There's definitely the potential for channel congestion if we start to limit our ability to broadcast safety messages to certain parts of the spectrum. If we're limiting the parts of the spectrum that we're able to broadcast in. So a quick update on where we are here in Columbus. At this point in time, all of our roadside equipment hardware has been installed. We're actually in the process of, getting all of those roadside equipment configured. And right now we have about 200 OVUs installed out of 1,000, and the goal being obviously more than 1,000 by middle of November. So far, we seem to be on track for reaching that goal, but we'll kind of wait and see. Some of that depends on how a big part of that depends on how well we're able to reach out to private participants and getting, vehicles equipped with onboard units. That recruitment is going to start here in July, with private installation starting in middle of July. And I guess I forgot to mention that we are currently installing on public fleet vehicles. Our go live date is on October the 1st, around October of 2020, and at that point we'll also be collecting data that's going to be used for performance evaluation. After roughly 6 months of the system being live, we're going to be using our data to perform a evaluation of the performance of the system. And also at that point, the system will continue to operate. Drivers will have the option to either keep the OBUs in their vehicles at that point, or they can have them uninstalled if they wish to do so. But the long-term plan is to have the system continue to be operational even after the period of performance for this project. So on that note, that brings me to the end of the presentation.
Fantastic. Thank you, Chris. Great presentation. So before moving into the Q&A period, I would like to remind attendees to enter your questions in the question box on the GoToWebinar platform. And also you can download a PDF version of the presentation from the handout box on the dashboard. So first question, how do you see this technology being translated into a tunnel environment?
So I see we're starting off with a very interesting and not an easy to answer question. But I guess I can start off by saying that positioning in general is a challenge for connected vehicle systems, even in an open air environment. In almost all cases, our high precision GPS are coupled with accelerometers and gyroscopes, and we can use that to obtain a more accurate position. But this technology, the GPS and accelerometers and gyroscopes alone, those wouldn't allow operations in a tunnel. I guess I'll go on a quick side note here. Many applications actually require a certain level of positioning accuracy to operate, and they won't function if positioning is not accurate enough. Obviously, that's going to be an issue in tunnels. Now, it's important to remember that at this point in the evolution of the CB technology, warnings that are issued by these systems are only intended to, I guess, supplement the driver experience by raising awareness in certain situations. And the driver shouldn't rely on these warnings at this point. But and regardless of what the vehicle actually ends up providing to the driver is ultimately responsible for the control of your vehicle. Now, going back to the tunnel question, that's obviously a greater challenge than the one that we're currently facing with the open air environment. It would likely require different types of technology to determine positioning. There's a couple of different ways that you could potentially do it. One way I'm thinking is potentially through triangulation based on relative signal strength of fixed radios located throughout the tunnel. Alternatively, if we start to consider the potential of autonomous vehicles and all of this, that have radar and lidar sensors mounted on the vehicle, they could, an AV could more precisely locate itself based on the detection of like fixed objects that have known locations throughout the tunnel, and it can just position itself that way. Now, to my knowledge, I don't know if any of those are being done at this point, particularly for connected vehicle applications. But those are some ways that could potentially work in a tunnel environment.
Thank you. Have you looked at human factors aspects of using an interaction with the OBU?
I'm sorry, could you repeat that one?
Sure. Have you looked at human factors aspects of using an interaction with the OBU?
Sure. So obviously there is a human interface with the OBU. So human factors is something that is important to consider in the when you're doing system development. Obviously, we have to determine what is the interface going to be audio? Is it going to be visual? Is it going to be haptic? What should the icons be? What should the icons that we display to the driver look like, and what does the sound like? We worked closely with one of our vendors to actually come up with a set of symbols, and we tried to be as consistent in the application of the symbols as possible. And if you recall, partway through the presentation, I actually showed some of those symbols on the V2V and V2I slide. some of the other human factors things that we had to consider were things like perception and reaction time, and you know, those are going to be important to consider when you're trying to determine when to issue a warning to a driver. So it's certainly important to consider it's certainly important to consider these various human factors components in the design, you know, for those reasons.
Perfect, thank you. Next question, are there related connected vehicle projects in and around the Columbus area that will leverage Smart Columbus?
So the answer to that question is there is another project located up in along the US 33 corridor, and that's both in that's on 33 and in the city of Dublin and in the city of Marysville. And the two projects are, although separate, are very much related to each other in that they're going to be broadcasting quite a similar number of the same types of messages. Drive Ohio, which is, you know, the body here in the state of Ohio that's sort of spearheading the deployment of these systems in the state, you know, they're very determined to make sure that, you know, to ensure interoperability between all the systems that are being deployed here in Ohio. So yeah, we're working with them very closely to ensure that, and we are actually one of the consultants on that project as well, on the US 33 project. So we're doing our absolute best that we can to ensure interoperability between, you know, what's being deployed in Columbus and then up in Dublin and in Marysville along US 33.
Perfect, thank you. Next question, two questions. Which vehicles will be using the OBU? And if you can disclose which organization are involved.
Sure, I can go into a little bit of detail there. So we are essentially deploying 4 different versions of the OBU. One is going to be for light-duty vehicles or private participants, and that includes, so I guess the light-duty vehicles include some private participants and some public fleet vehicles. Then there would be our transit vehicles. That's going to be all of the operational transit vehicles. They're going to be equipped for our local transit agency, which is COTA, Central Ohio Transit Agency. We have a private partner that we are going to be putting our heavy-duty vehicle OBUs on for our freight vehicles. And finally, emergency vehicles. We're going to be partnering with both the Division of Fire and Division of Police in Columbus to be deploying OBUs on those vehicles as well. Now, the differences between those vehicle classes is the applications that will be deployed on them. So obviously all of our light-duty vehicles are going to have all our V2V and V2I applications on them. Our emergency vehicles are only going to be having the emergency vehicle preemption. Transit vehicles will have transit signal priority on them. And our freight vehicles are going to have the freight vehicle priority.
Thank you.
And I guess the only other important thing to note there is that all vehicles that are going to be out there are going to be broadcasting safety messages. So just because you're in a light-duty vehicle, you can still receive information from all the other vehicle types, and you can get V2V warnings based on these.
Thank you very much. We do have additional questions. However, these will be answered directly by Chris. Thank you very much for answering all your questions. So we are at the end of our webinar session. Thank you for your time. Please feel free to follow up directly with Chris via the contact details shown on the screen. And I would like to thank all attendees for joining today. And again, big thank you, Chris, for presenting today.
Thanks, everyone, for attending. I look forward to responding to your messages.
Thank you.